Okay, so here it is. So we have yeah, this is saying so that 1 liter of water is 1 kilogram. And remember, 1 liter was 1 decimeter cubed. Um, and that's how we kind of defined it, right? It was a decimeter by a decimeter by a decimeter was my 1 liter. So that means, for example, that 1 milliliter of water is 1,000th of a kilogram. Oops. So if I look back up and I see, right, the ratio between a liter and a milliliter, oops, sorry, the ratio between a liter and a milliliter was 1/1000th. So 1 milliliter of water is 1/1000th of a kilogram. And we call this a gram. So that's what a gram is called. Okay, it's 1 milliliter of this water in its densest state. Okay. All right, so last but not least, talking about temperature. Here, what we can see is, so in degrees Celsius, we have a smaller scale. So on the left here, this thermometer is measuring degrees Celsius. So in Celsius, what's really nice is that on like a scientific scale, it works very nicely and conversions are nice. 0 degrees Celsius is where water freezes. 100 degrees Celsius is where it boils. So we're thinking of, the 0 to 100 range is, water between freezing and boiling, right? But what that means then is then on the human scale, things are very small. So here, notice from water freezing to boiling in the Celsius, we have 100-degree change. And in the Fahrenheit, we have 180-degree change. And what that means is in Fahrenheit, in just talking about the change in a degree, measures a subtler change than 1 degree of change in Fahrenheit. And so this is one thing you'll notice maybe from people that standardly use the metric system, which actually most of the world, especially as far uses the metric system in general, and especially in terms of temperature, we're basically the only ones that use degrees Fahrenheit. But there is one advantage for using degrees Fahrenheit and talking about the weather here. You're better able to kind of assess what a temperature means. So the difference between 1 and 2 degrees temperature change here really does not mean much as far as what you're going to wear for that day. However, on the Celsius scale, just 1 or 2 degrees can make a very large difference. All right, so I just want to talk about deriving, doing a conversion from degrees Celsius to degrees Fahrenheit. So we'll set up this, a way to kind of derive this conversion. And basically what we're going to do is we're going to start by setting up a ratio. And so remember we said there are 100 degrees Celsius change for each 180 degrees of change of Fahrenheit, right? So when the degrees in Celsius change by 100, the degrees in Fahrenheit are changing by 180. And so this gives us a nice ratio of 100 degrees Celsius to 180 degrees Fahrenheit, or 1 degree Celsius for every 1.8 degrees Fahrenheit. Right, so we're just setting up a ratio between these two things. So we have like a relationship in scale here. We also kind of need a point to start off from. And so remember, if C is the temperature in degrees Celsius above freezing, then the equivalent temperature in Fahrenheit is, so when in Celsius, when we're a certain number of degrees above freezing, that starting point is 0, right? 0 is where we start at freezing. But in Fahrenheit, we're starting at 32 is where freezing starts, freezing water. And so for every 1 degree, so we're going to start at 32 degrees to get above freezing. And then for every 1 degree change in Celsius, there's going to be a 1.8 degree change in Fahrenheit. And that gives us our conversion. So basically, we just start with this ratio of for every 1 degree of Celsius, there's 1.8 degrees of Fahrenheit change. And then we just shift up so that to start Fahrenheit at freezing, we just add that 32 degrees. Okay, and so this formula makes it really nice to convert from degrees Celsius to degrees Fahrenheit. We can just go ahead and plug in 37 for C. So we can do that. So that's 32 plus 1.8 times 37 should be, I think, 98.6 degrees Fahrenheit. So this is roughly body temperature. And so body temperature in degrees Celsius should be about 37 degrees. And if we are talking about converting from Fahrenheit to Celsius, well, I want to take this 1.8 C plus 32, or 32 plus 1.8, and I want to set it equal to this 68 degrees Fahrenheit, and I'm going to solve now for Celsius. So that means I'm going to take 1.8 C, so I'm going to subtract 32 from both sides. Oops. And I get 68 minus 32, and then I'm going to divide by 1.8 on both sides. And I think if I do this out, I should get 20 degrees Celsius. Okay. So just solving this conversion formula for C will give you a way from going from Fahrenheit to Celsius. Okay, so last but not least, I want to talk about dimensional analysis. And this is basically using conversion among units. And I mentioned it briefly when we were talking about going from, I think, feet to feet squared. You can see a sort of dimensional analysis there. It can also be useful just from going from different units of the same dimension, so same type. So for instance, if we want to convert the 17 feet to inches. What we can do is say, so we have 17 feet, and we can take this 17 feet, and we know that, well, there are 12 inches for every 1 foot. And what dimensional analysis lets us do is kind of use the units like variables to make sure that we have done a proper conversion. Okay, so notice here when I write out all of my units, my feet cancel, and I get 17 times 12 inches, and that's 204. So that tells me that this is 204 inches. What's nice about this dimensional analysis is a few things. Actually, it's a very useful thing in mathematical research. Basically, you always want your equations to balance. You want your units to work out, and sometimes that can help you solve for things that you might not have otherwise known. The other nice thing is it does help you kind of keep track of whether you found what you're looking for, I suppose. Okay, so let's try another example. Let's see, 4,286 grams. We want to convert it to liters. So this is 4,286 grams. And then I'll use my conversion that I know that 4,286 grams. For 1 milliliter, there is 1 gram. And for one, but I want to go into liters, right? So for 1 liter, there is 1,000 milliliters. Okay, and so now notice these milliliters cancel since everything's multiplied, and the grams cancel, and I'm left with 4,286 over 1,000 liters. And so that's 4.286 liters. Okay. So as you can see in this example, and you'll see in the next one as well here, converting feet squared to acres, it's really helpful. Using dimensional analysis is really helpful when especially when you need to convert to do multiple conversions. So here we have 25,375 feet squared. And what we want to get to is we want to get to acres. And so we haven't put this conversion up before, but maybe I did earlier. But 640 acres is a square mile. So we have 640 of these per 1 mile squared. So then we just need to know how many feet squared do we have in a mile squared, right? And it should be 27,878,400 feet squared in 1 mile squared. These are all multiplied. And so my feet squareds cancel, my miles squareds cancel, and oops, put it down here. And I get 25,375 divided by 27,878,400 times 640 acres. So now if I do this computation, I think I should get about 0.58 acres. It's rounded. It's not exact. Okay. So just a couple more examples. So here's an example where I have some mixed measurement. So I have 19 feet and 4.5 inches. So this might be helpful to convert all into one unit. So 19 feet, 4.5 inches would be helpful to put in terms of only inches. So I can multiply that 19 by 12. So that's 19 times 12 plus 4.5 inches. And that should be 232.5 inches. And I want to convert this into meters. And so I'm going to do that via centimeters because I know there are 2.54 centimeters in 1 inch. And so I take this 232.5 inches and I multiply it by that 2.54 centimeters in 1 inch. And then, of course, to get from meters to centimeters, there are 100 centimeters in 1 meter. And so now canceling my units, this is 232.5 times 2.54 all over 100 meters, which I think is 5.9055 meters. Okay, so the last example that I think is probably one of the more helpful cases of using dimensional analysis is especially with rates. So rates lend themselves really nicely to this kind of computation. So here we want to go from miles per hour, so NPH is miles per hour, to feet per second. So we're starting off with 200 miles per hour, and it really helps if you think about a miles per hour is literally just miles divided by hours. And I want to convert this into feet per second. So let's use the fact that we know there are 5,280 feet in 1 mile. And the fact that there are 3,600 seconds in 1 hour. So that's just 60 times 60, I think, right? It should be 3,600 seconds. Okay, and then again, my units should cancel nicely. So my hours cancel with my hours, my miles cancel with my miles. So if I did everything right, I should be left with feet over seconds, right? And that's what I do have here, I think. So then simplifying this is 200 times 5,280, all divided by 3,600 feet per second. And that should be 293 1/3 feet per second. Great. So I think what's really nice about this dimensional analysis is it can be sometimes difficult to remember, do I multiply by 5,280 or do I divide by 5,280? And this way of thinking, okay, there are 5,280 feet for every mile. And then just putting the units in the right places so that things cancel is really helpful when you're trying to convert between different types of units, okay? And so that's what we're referring to as dimensional analysis. Okay, so here are some problems at the end of the section that you might want to take a look at and talk with me about. I think a lot of them talk about the ratio between uh, units in length versus their corresponding units in area or volume. And so the thing to think about with each of these problems is the example that we saw above, which is, when I go from, so there are, so an inch is 1/12 of a foot, but a square inch is not 1/12 of a square foot, it's 144th of a square foot. So I think this concept of this ratio being squared is what a lot of these problems are kind of referring to. Okay, so in the next section, we're going to talk in more detail about length and area, but more generally and not with regards to specific units.